Hi class, I'm making this video in the middle of our Labor Day holiday. Uh, so we had that business with the lost Zoom class. The Zoom link didn't get to you by email, and we ended up canceling that class. So I'm going to make a couple of YouTube videos to sort of fill in the gaps for the week of September 1st and 3rd. We're concerned with a single topic for this video, the notion of a difference quotient. Now, what's that? Well, when we have linear functions, here's the graph of a linear function. It doesn't matter which pair of points we choose. When we find the slope, we get the same value. So if this is P and Q, we find the slope, and then down here is another P, call it P prime and Q prime. They can be in a different place and closer together or further apart. If we find the slope, you remember that's yq minus yp over xq minus xp. We always get the same value. That's because of similar triangles. If we compare this vertical change with this horizontal change and make a ratio, it doesn't matter which pair of points we choose. When we form the quotient, we get the same answer. Well, we have nonlinear functions. Most functions are nonlinear. So in that case, you remember the graph of a function has to pass the vertical line test. So no matter where you draw a vertical line, you're supposed to meet the graph in just one point at most. So clearly it makes a big difference. I mean, if I pick this point and this one and find the slope, and then you pick this one and this one and find the slope, you'll get a different answer usually. But we're still interested in these quotients, even though they vary. Typically, when we change from two points to two different points, this line doesn't have the same slope as this one clearly. But we're still interested in comparing the amount that y changes by the amount that x changes. So let's have, to show how this might occur, I want to build your intuition for this before we look at our math examples. So first example is from real life, just so you can get a feeling for this. So suppose you're driving along the interstate, and your speedometer's broken. And you look at your watch and it's 118. And you pass a mileage marker that says 38 miles. So if this is I-85, you remember these distances are measured from where the Interstate 85 originates, which is actually here in Montgomery at Maxwell Air Force Base, near there. And then at 148, you pass the mileage marker that reads 75 miles. what's your average speed? That's a difference quotient. So we compare the change in distance with the change in time. So your average speed would be change in position over change in time. Okay, so the change in position is the new position minus the old position. So it's 75 miles minus 38 miles. And here's the change in time, 148 minus 118. So this distance here, 75 minus 38 miles, is 37 miles. Now, a half an hour passed, right, from 118 to 114, 1/2 hour. So invert and multiply, and you get 2 times 37 miles per hour, which is 74 miles per hour, right? Okay, so an interstate highway, you're probably okay if the speed limit is 70, because you're just slightly over that. If it were 55 miles an hour and you're doing 74, you might get a ticket. Okay, so that's our first example. So this is the same formula, yq minus yp over xq minus xp. All right, now let's look at some math examples next. And they're going to be based on the same function, so that to save us time, I'm trying to keep this presentation short. So here are two math examples. Let's see, maybe three. So here are math examples of difference quotients. And they're all going to be based on now, I guess even the previous example was a math example, wasn't it? It's kind of redundant to say math examples. Let's just say examples. On the function y equal f of x equal x squared plus 2x minus 3. Now the graph of this is a quadratic function, by the way, obviously, and the graph passes through the points of -3 and 1, it turns out. It's a parabola. So our first example uses the points so we're going to look at f3 minus f2 over 3 minus 2. F of 3 minus f of 2 over 3 minus 2. Okay, so we have a point P, 3f of 3, f of 3 and 2 f of 2. And what we're trying to find is the slope of this line that joins these 2 points. So what's the slope of that green line? Okay, well it's pretty easy. F of 3 is 9 plus 6 minus 3, that's 12, right? And f of 2 is 4 plus 4 minus 3, which is 5. 3 minus 2 is 1, so it's 7 over 1, which is 7. Okay, so the slope of that green line is 7. Now, I'm not sure any of you will take calculus. You might take the survey course, but in calculus what happens is we have a fixed point P, and we imagine that this point Q gets closer and closer to P. And we're interested in what happens to this green line as the point Q slides down the curve and gets really close to the point P. So the difference in the x values tends to be quite small. Second example is this. F of 2.01 minus f of 2 over 2.01 minus 2.00. So now the point Q has moved much closer to the point P. This is the new Q, much closer. Okay, now to save time, I use my calculator to find f of 2.01, and I'm not going to work that out for you, I'm just going to write what it is. So it's 5.0601, and then f of 2 is still 5. And when we subtract here, we get 0.01. Now, when you're doing these calculations, you don't round off. That's very, very important. These are the significant digits. These digits are the important ones. Okay, so even though this digit is way out, it's the fourth decimal digit. It's an important digit. You don't round off. So when we subtract, we get 0.0601. We divide by 0.01. So to divide by 1/100th, we shift the decimal point 0.2 places, and that gives us 6.01. So when the point Q moved from x equal 3 to x equal 2.01, the difference quotient changed from this value to this value. Okay, now these are what we call numerical difference quotients. So we assign specific values to x. Here the values are 2 and 3, here they're 2 and 2.01. We also have algebraic difference quotients, and for those we don't assign particular particular numerical values. So let's now calculate algebraic difference quotient. So f of a plus h minus f of a over h, in which we don't specify values for a and h. The numerical values of a and h are not specified. Okay, so in the previous two examples, in the first one, a was 2 and h was 1. 2 and 1 are 3. So we found f of 3 minus f of 2 over 3 minus 2. In the second example, a was 2 and h was 100th. Now I need some more room to do this. So I'm going to break it into 4 steps for you for clarity. So what I'm going to do is find this function value, and then this one, and then I'm going to subtract the two, and then I'm going to divide the difference by h. Okay, so 4 steps. You can do it all in one big step, but it'll be easier to follow it if we do like this. So number 1, f of a plus h. So you remember how function notation works. So we've defined our function here. Whenever we have f of an expression, the way it works is that expression replaces x wherever it occurs on the right. So for f of a plus h, we replace this x by a plus h and this one by a plus h. Now we have to multiply this out. Now, I hope you remember when you square a binomial, you get a middle term. So this is a squared plus 2ah, that's the middle term, plus h squared. And we use our distributive law. And we have minus 3. Now, f of a is much easier. You merely replace both of these x's by a's. So it's a squared plus 2a minus 3. Now we're going to subtract this value from this one. Now, this looked complicated. We have a bunch of terms here, 1, 2, 3, 4, 5, 6. But when we subtract these 3, we get loads of cancellation. Remember, I'm subtracting all 3 of these terms from these 6. So a squared minus a squared is 0. 2a minus 2a is 0. Remember, I'm subtracting all 3 terms. Now be careful, negative 3 minus negative 3. I'm subtracting negative 3. So there's a double negative involved there. Okay, so that was nice. We had 9 terms, 6 here and 3 here, but now only 3 of them are left. So 2ah plus h squared plus 2h. And now we notice something else. The h appears in each term. So we have a factor of h here. If we think of h squared as h times h, we have an h there and we have an h here. So we can factor out the h. That'll help us in the final step. So we removed one h from each of these three terms. Now we're ready to divide. So we have, this is our numerator. This, and it should, that's right, that's correct. And this is our denominator. Now our numerator is a product. It's this factor times this factor. You can cancel products from fractions. So when we cancel that, we end up with 2a plus h plus 2. Now, this is very, very useful. This answer confirms the previous two answers. So you remember in our first calculation, we had f of 3 minus f of 2 over 3 minus 2. So our a was 2, our h was 1. So if you put a 2 there and a 1 there, you get our previous answer. 2 times 2 plus 1 plus 2, that's 7. 4 plus 1 plus 2 is 7. In our second example, we had 2 and 2.01 here. So our h was 100th and our a was still 2. We've got almost the same thing. 2 times 2 is still there and 2 is still there. And now we have a 0.01. So we get 4 plus 2 plus 0.01. In a sense, when we do this calculation, we're finding all possible difference quotients for this function. In other words, we can allow P and Q to be any 2 points on the graph, and this tells us at a glance what the slope of the line is between those points. Okay. Now this for college algebra students, this is quite challenging, but that doesn't mean you shouldn't study it. You need to go over these details and make sure you understand each separate step and how they all fit together. And you certainly need to know how to do numerical difference quotients. Okay, thank you, class.